Now you may ask, in humans, what type of cleavage do they have? It's usually considered to be meroblastic, and the only reason why that is we have the evolutionary history of being amniotes, so we're related to the reptiles. So we form a disc of cells. We'll go over that shortly. All right, so what we see here is we form a blastostage with a blastocyst. Okay, now students, and I understand why. Here's an ovum. There's an animal pole and a vegetal pole. This vegetal has most of the yolk. This animal pole is pigmented. Since the egg has a lot of yolk, when it's released, it rotates downward. So then what would happen is the vegetal pole would be in contact with the substrate. And that's great because then you have this pigment on the animal pole, so any fish or predator swimming above wouldn't be able to see those eggs very well because they blend in with the substrate. The other thing is it gives some UV protection as well to the DNA that's in there. So this is an ovum. This is an 8-cell stage. 4 here, 4 below. Not really easy to see. So you can see here, 4 there, 4 there. Notice the animal pole is still here, vegetal's there, but that distinct line of pigmentation is disappearing because of all that cell division. Okay? Here's the blastula stage. We can't tell if there's a ball cavity inside of the blastocell. This, many cells. So most students say they have great difficulty this versus this. And that's because on the lab exam, you're looking at the vials. When you're in lab today, or this week, you're going to look at the vials with these things in them. It's kind of hard to see. So on lab exam, too, when you're rotating, students struggle with this because you have to make scope focus, you have to rotate this vial just right. So on this lab exam, you have images, it should be very clear, okay? So that's how you'll tell a blastula versus an ovum, okay? And then what happens is because we have this cavity within here, the cells can migrate inward. It's not a solid ball of cells anymore. And as they migrate inward, they form 3 germ layers. So we start to form the primitive gut. Now this is a frog. A chordate. Is that deuterostome or protostome? Deuterostome. So what's the first opening that's formed? The anus. So we actually form the anus. So what happens here is this is the primitive gut forming, called the archenteron. But what we form here are 3 germ layers. The endoderm in yellow, the mesoderm in red, and the ectoderm in blue. So the endoderm is going to give rise to the GI tract and outpocketings. Mesoderm, you can think of that like middle, muscle, bone, and ectoderm, the outside, and the nervous system. And here's the gastrostage here, and the opening here is called the blastopore. This opening, that first opening there, and we see the opening here of the blastopore, and we see yolk inside. So the gastrula stage is easy to identify because you'll see this ring like this, that's the blastopore. So there's never any difficulty identifying the gastrula stage. The neural stage, we're starting to form that dorsal hollow nerve cord, brain at the anterior end, spinal cord leading posterior. We basically have these cells migrate upward to form a tube, so that's the dorsal hollow nerve cord. Okay? And we had a notochord underneath there not shown there, but that's another feature of a chordate. Okay? And that looks like a groove on the top. And it's pretty obvious to tell here, that's that neural tube forming. So you'll have no trouble identifying that. This just shows some structures. They do point out the notochord here, and then here is what it looks like. Now, it's a lot larger opening there than at this end. So do you think this is anterior or posterior? Anterior because of cephalization, right? That's where the brain is forming. So because of cephalization, it's going to be larger, right? So there's a question where I could ask you, would this be the posterior end or the anterior end? By looking at this structure, I could ask you to identify it. I could give you these raised stages and say put them in order chronologically. And then since it's multiple choice, I would then have, I'd have the 4 stages numbered or something, and then choice A would be 1, 2, 3, 4. Choice B would be 1, 4, 3, 2. So the fastest way to answer that type of question is provide the answer yourself, and then look for the answer that matches. If you go through every possibility of multiple choice, it's just going to take too long. Okay, make sense? So that's a test taking strategy. It just shows you that dorsal hollow nerve cord, and there's the notochord. And if you want, I didn't give you the URL for this. I can post it on DSpace, but you can actually see that change in membrane potential as a wave. For the chick egg, huge amount of yolk. Okay, so there's a small disc of cytoplasm up here. All right, and that's where all the mitotic divisions are going to be occurring once fertilization has occurred. Now, this egg is fertilized before it is laid. Okay, so what happens is the rooster and hen mate, the sperm go off the oviduct, and as the egg is being released, the sperm would swim off the oviduct and fertilize this. And as it goes past the fallopian tube and that, the egg shell gets released around it. So the sperm aren't swimming through the shell membrane, the egg shell, right? So this just shows you we get all the divisions up here at the very small disc, and so we end up with basically layers of cells like this, the epiblast and hypoblast, that's going to give rise to things. Okay, so the hypoblast will give rise to some extra embryonic membranes, and the epiblast to the organism. Okay, and in the case of forming the 3 germ layers, cells migrate inward, and they just, again, if you had the balloon, instead of pushing your finger in, you'd take your hand like this and go down that balloon, and you'd see a groove, because the cells migrate in a groove here or a streak. Okay, that forms the 3 germ layers. You're not going to see these raised stages in this early stuff here, so I just want to point out to you, we do form the 3 germ layers, okay? The endoderm, the mesoderm, and the ectoderm, and they maintain similar relationships where the ectoderm is on the outside, the endoderm is on the inside, and the mesoderm is between them. So they have the same relationships. And then, please make a mark on this. The colors here have no correlation with the colors here, okay? I take that back. I changed this. They do have a correlation now. They used to be from the textbook, and they didn't have any correlation. I'm like, why did they do this? But I actually changed it now. They do have correlation. So blue here is the ectoderm, mesoderm is here, yellow is there. I forgot that I actually changed this. So there's the correlation. So endoderm, the GI tract and outpocketings, mesoderm, the notochord, skeletal system, muscular, and ectoderm, the outside skin, and things like eye and the brain, okay? I would never ask you, does the toothed enamel or the adrenal medulla come from the ectoderm? I would do more general type questions, okay? The nervous system, things like that, okay? Because it's just too many small details, not so crucial. In terms of development here, we'll have extra embryonic membranes. Those membranes are outside the developing organism, okay? Now in this case, those extra embryonic membranes can only come from this developing organism. In the case of humans, when we talk about the placenta, we'll say it's composed of both maternal and fetal tissue, but in this case, it's only fetal tissue, right? So we'll see the 4 membranes. Several of them are easy to see. The amniotic sac, which forms the amniotic chamber where we have fluid filled. So if you've heard about a woman, the water has broken, the amniotic sac has ruptured, and amniotic membrane is being released. If you've heard about amniocentesis, that's where basically they do an ultrasound to follow the progress of the needle. They basically go through the abdominal wall, insert it, and then go past the uterus, and then they go in, and then they pull out a little amniotic fluid, and then cells are being sloughed off in that amniotic fluid, and then they can do some genetic tests of that. Okay, so that's what amniocentesis is. There's now possible methods to completely avoid amniocentesis because that has potential risk to the developing embryo. All right, so we have amniotic sac, we have an allantoic sac here, or allantoic membrane. All right, right here, and that's going to be filled with nitrogenous waste. So this is a chick that's developing, limited amount of space in that egg. What form of nitrogenous waste do you think would be? Ammonia, urea, or uric acid? uric acid, because then you're not having to spend all this water to dilute it to prevent the toxicity. So indeed, you can figure out a lot of things by general principles and not have to memorize a lot of details, okay? So we have the amylose sac here. We have a yolk sac here. On the chick embryo, you're going to see it spreads over the egg yolk. It's filled with blood. That's where the first blood cells are forming. And you'll see blood cells moving back and forth. And I have a video, if there's time, I'll show you of this. And you'll see it in lab. And then outside all of this is the chorion. And then clearly this has to undergo gas exchange throughout development, right? So most of the gas exchange will be at the amylocois, because it gets pressed up near the shell as it's developing, and the chorion, okay? And humans have, of course, the amniotic membrane. They have a chorion as well. When they talk about chorionic nuclei sampling, that's going through into the placental tissue, and they're looking for the chorion. And basically that's fetal, so when they do the genetic testing, they can get the chorion. And that's part of that chorionic nuclei sampling. Here shows you the chick embryo here, developing eye. You can see various portions of the brain forming. The notochord is here. You can see vertebrae start to form, a beating heart here. There are limb buds, both legs and wings forming. And then this just has been pulled away, and the GSIs will demonstrate how you do this. So here's the allantois. It's getting quite large, and that's where we get some gas exchange. The amniotic sac is here, surrounding that developing embryo, and the chorion isn't visible because it went over the egg yolk in that, along with the yolk sac. This just shows you a cross-section through a slide. You see the dorsal nerve cord, the notochord. So on the lab exam, I could have this sort of image and just actually identify this, or I could say, would you find, so this is dorsal nerve cord, would you find the same orientation of the nervous system in a cockroach? No, because where's the it's ventral, right? The nervous system is ventral in the cockroach, so it's not dorsal. Okay, let's look at some images here. Here's the female, here's the ovary here. So there is actually a membrane that surrounds the ovary that directly connects to the fallopian tube. So in rats, if this is a fallopian tube or oviduct, here's the ovary. Those ova can't escape into the abdominal cavity typically. But in humans, that's not true. In humans, there's the ovary. Here's the oviduct and fallopian tube. Has some finger-like projections like this. So in humans, when ovulation occurs, the secondary oocyte gets released, along with the surrounding cells, don't forget, into the abdominal cavity. But because this, during signals of the cycle, these fingers actually sort of grow up along the surface here, and they will recognize the developing oocyte there, and they'll pretty much be pretty close. So very seldom does it get lost in the abdominal cavity, but sperm have to swim up here, and if there's successful fertilization, it's usually the upper third of the oviduct. And that's because as it migrates down the fallopian tube for implantation, you're undergo those cleavage reactions. And the length of time, if it was in the middle third, by the time it gets there, it wouldn't have done enough cycles of mitotic division to be able to successfully implant. But that's why it's usually in the upper third. Okay? And in humans, you can get what's called ectopic pregnancies. So what happens there is the sperm fertilizes the secondary oocyte, and then instead of going down the fallopian tube and implanting in the endometrium, it might plant, let's just do it here. Here's the GI tract, that's the anus. Here's the abdominal cavity. It might actually plant in the wall of the large intestine, but from the abdominal side. And a few years ago, there was a case just like that. And to me, it's amazing that you can actually form a placental connection. So the hormones and such are enough that they literally form a placenta here with this intestine, and the fetus starts to develop. So not too long ago, maybe 5 years ago, there's a patient at Kaiser that had this happen. Ectopic pregnancies can occur. They can implant in the fallopian tube. This is very rare, but actually far enough along that they were getting a court order enforcing the woman. Now, could she give vaginal birth to this? No, because it's not in the birth tract at all, right? So they have to do a C-section, and so they got a court order to do the C-section to save the developing fetus, and also to potentially save the mother's life, right? So anyway, here shows the ovary, highly vascularized. We have those, in this case, multiple ova being produced. They'd be released into the fallopian tube here. Small white coils, so the sperm have to go up here, into the vagina, past the cervix, into the uterine horn, and then fertilize way up in the upper third. But as they migrate down, there's cilia here that beat, that create a current that pulls this downward, and the sperm has to swim against that current. They fertilize up here, and by the time they successfully have completed the mitotic divisions in that, they can then implant along this uterine horn. So in the rat, we can get 6 to maybe 8, 9, 10 per uterine horn. We see that here, multiple embryos implanted here, one uterine horn here. And we will oftentimes find where only one uterine horn has implantations. That may be because this ovary didn't ovulate. Maybe the uterus here is not viable, but that's a fairly common feature, okay? So, any questions about that? Yes? So humans typically only have one uterus, and it looks more like this. And I think I have an image of this. With the cervix here, that's the basis of the diaphragm for black sperm from getting in here. And then the fallopian tubes comes off like this. And then this is the uterus here. And the lining is the endometrium. And that thickens. That's what gets left off. So the sperm has to go through the vagina, past the cervix, into here, then swim up. Now, occasionally humans can have what's called a bifurcated uterus. I had a student once, his wife had a bifurcated uterus. And so they had tried for years to have a successful pregnancy, and they were not successful. Well, they were eventually, but they were going through a divorce. So, yeah, bad timing. All right, it's just an aside. Anyway, here's the placenta, both maternal and fetal tissue. Here's the developing embryo. There's that amniotic sac. There's the umbilical cord there. Placenta, developing embryo there. Make sure you know the difference between males and, deuterostomes and protostomes. Dr. Firestone will talk a bit about human development. We don't have time, but there's various images here. 6 weeks old. This shows you the amniotic sac there. Yolk sac there. We haven't quite formed the placenta yet, but we will. This shows you birth. Head typical. There's the placenta. So a large mass. This is my nephew. This is not my nephew. Anyway, so images like this. But I'd like to take the next few minutes to show you a few movies. Okay? So these movies are sort of for your general interest to hopefully spark your interest and keep you motivated for studying for the lab exam. So let's do this one here.
Inflatable tubes that enable them to get to those hard-to-reach places.
This is springtail grooming.
To help them get around through the leaf litter, these springtails, as their name suggests, have a rather novel way.
Also defense.
They have a tiny two-pronged lever beneath their abdomen. One small flick from it can catapult them 6 inches, some 15 centimeters, into the air. It's the equivalent of a human being jumping over the Eiffel Tower.
That's pretty impressive. Then they
If they happen to land upside down, well, they
remember they have the exoskeleton protection.
They use their grooming fluid dispenser to stick onto the ground so that they can pull themselves back onto their feet.
So that doesn't right itself. This is the giant earthworm.
Worms can only live in a moist environment, but they are found in soils of every continent except Antarctica. This small valley in southern Australia is home to one of the rarest and the most extraordinary of all earthworms.
You can hear the earthworms in the soil as you walk up to them.
Because I can hear them. Those gurgling noises, believe it or not, are being made by giant earthworms as they squelch along their water-filled burrows.
Okay, I personally find this stuff interesting. I guess people are like, ugh. It's pretty cool.
The vibrations of my footsteps are enough to stir them into activity.
And you can see the segments there very clearly. The segmented worms.
They never come to the surface, but in places where there's been a small landslip, you can sometimes find their burrows. They are over an inch in diameter, and in them, if you're very lucky, you may occasionally find one of these.
An egg case.
It is one of their egg cocoons, and it's enormous. If I hold it up against the light, I can see the young worm inside.
Closed circulatory system. You see hemoglobin there.
For this to develop, and when the young one finally does break free, it's already 20 centimeters long. Huge. It will take a further 5 years to reach full size and become this remarkable creature. So the question is, how long is a giant earthworm? Well, it's not an easy question to answer. The fact of the matter is, they're rather delicate creatures, and they break. If I was so unfeeling as to try and stretch it, well, I guess it might stretch to a couple of meters, almost 6 feet long.
Okay.
How long they...
This one ties together reproduction and arthropods. This is behavior. I mentioned that the arthropods have complex behavior, especially the hexapods.
He's doing very well. She's not attacked him. Yet.
That's a male on the left trying to entice the female to mate with him. You've seen these rituals before. They look very different from humans, though.
She spreads her 8 legs. It's a clear invitation to mate. He checks the taste on his legs again and decides to go further.
So the trail, that web is actually modified so she can tell
After
the
mating, he
gender.
has at best a
That's the-
50-50 chance of staying alive. But nothing ventured, nothing gained. He moves in and delivers his sperm.
Uh-oh. We have a
But
problem.
his luck runs out. Virgin she may be, but with mating completed, she grabs him and binds him in silk.
Food for later. So there you had to see where there's mating behavior, complementary behavior, timing, and then in this case the male unfortunately was killed by the female. If she's already mated, then for certain she usually kills
She
them.
will eat him later.
I've talked about how larval forms have different
Unit large.
environments often
Some
adults.
rise to the surface and struggle out of the skins in which they lived as larvae.
Along this river, sometimes they have snowplows to
At
clear the
first
roads when
there
these
will be
things emerge.
one, soon there will be millions.
And of course, flight we talked about, complex behavior.
For 2 years they've lived underwater. Now they must fly to find a mate. This should be the climax of their lives.
It isn't.
The first to appear are quickly taken by predators. But soon the swarms are so huge
They just can't
that
eat
neither
enough.
fish nor birds can make any impact on them. The first mayflies to emerge in this mass hatching on this river in Hungary are all males. As soon as they free themselves from the larval skin on the surface, they take off and seek safety in the banks. And there they hang in trees and bushes, or indeed on my finger. And the reason they have to rest like this is because they still have to make one final molt.
See it molting?
Their wings that were transparent now have a handsome blue tinge, and the elegant
Attractive to
filaments at the end of
other
their abdomens
sex?
are even longer than before.
Longer tail, more attractive.
They're looking for mates, but they have a problem. They can't feed, for they have neither mouth nor stomach. They have to fuel their
They're very
flight
focused.
entirely from the reserves of fat that they built up when they were larvae feeding in the river.
But that fat will only last them for about half an hour of flight time. So the race to mate now becomes a frantic one.
And we thought we had it bad.
The females begin to rise to the surface, and the males fly up and down the river searching for them. As soon as they find one, they all pounce on her, competing to be the one to fertilize her
Okay.
eggs.
All right. So we'll stop there. Good luck studying. Next Monday, I'll have the slides. We'll go over it. And there's lots of these sorts of movies you can watch that make it a little bit more interesting.